Hi, welcome back to Programming Like It's 1979. We're going to be doing session 2 of Joachim Breitner's Incredible Proof Machine from the website incredible.pm. If you missed the first episode of this series, you should probably start there, and if not, let's jump in. Session 2 seems to be all about implication. All right, we have two givens. We have A, and we have a rule that says A implies B, and we want to prove B. So we're going to use I believe this is called, I should say, I know I make this disclaimer every time I talk about math and logic. I'm going to make it again. I'm not a professional mathematician. I'm not a logician. I am 100% positive that I'm going to make terminology mistakes during this video. If I do, I encourage you, I beg you, call it out in the comments below. I will take the feedback and try and do better next time. All right, we're going to use what I think is called the implication elimination rule. So this takes two arguments. Let's pull out those arguments here. It takes some x goes to some y. I'm thinking like a computer scientist. X implies y, and it takes an x. Well, if we put the x into this block, we get A. Now we're at A implies Y in our proof state. And if we plug this into here, I've really messed this one up. Let's pull out a new one. A implies B. Okay, so if we have A implies B and we have A, we can use those to get B, which is indeed the answer. Let's go on. Now we've got A, and A implies B, and B implies C. So we're going to have to chain, I think, some implication elimination rules. That should be our B. B implies C goes there. We've proven C. Great. They're really committed to this bit. I think here what the point of this level is, I like to ask myself didactically, what's the didactic or what's the word? That's not the word. What's the educational point of any given level? And this level, I think, is teaching you that if there are multiple paths to get to a solution, you can take whichever one you prefer. So let's take the B implies D path here. A implies B, B implies D, D is our goal. Great. Given A and A implies A, prove A. Well, we could use an A elimination we could use an inference elimination rule here, implication elimination. You know, I have to know, is it inference? It's implication elimination, right? I'm going to go look it up right now. I'll be right back. All right, Stanford Introduction to Logic does indeed say that it is implication elimination, not inference elimination. See, I told you I would make mistakes. Proven that. Let's go on to the next level. A implies B and B implies C implies A implies C. So this level is going to require us, I think, to use the implication introduction rule. So let's go ahead, because note that what we don't have here, right? We don't have an A at all. In fact, we don't have anything from the left-hand side of these implication arrows. So in order to even construct this, we're going to need, I think, to introduce an implication. So the implication elimination block is the first really complicated one we're going to look at. At least I think it's complicated. It's got all these parts, and it's got this funny shape. And the idea behind this funny shape is that as you introduce kind of sub-parts, like within the parentheses notionally, maybe you fit them kind of between this as like brackets. All right. So I'm going to try and work backwards here. The basic idea here, again, all my bad terminology, is this over here is the thing you're assuming. This is the thing you're trying to put on the right side of the implication arrow. So we've got the implication arrow. This is the thing on the left side. This is the thing on the right side. And the thing coming out is the whole kit and caboodle. So we want to prove A implies C. I'm going to hook this up. And what should happen is that X should change to A and that Y should change to C. And indeed, that's what happens. But I still feel like I'm really no closer to solving this. So what are we going to do? Well, there is, an important distinction here, which is now that we're kind of assuming A for purposes of introducing this implication only. And we have that A implies B. And we can use this A inside this proof, inside the brackets. So I'm going to plug this A into this implication elimination. That gives us B. We can take a second one. That gives us C. Now, when I plug this C in down here, we're going to solve the level. So before I do that, there's a mechanical thing here where the only way we can use this C is within the scope of this implication introduction rule, unless it comes out of, the end of it. If I were to introduce another one of these, plug this in here, right? Here's our A. This is not a valid proof because we've let the scope of this sort of escape our assumption. In fact, this line is red back here because it's telling us this is the thing you assumed and you've kind of let it escape the scope. So we're going to get rid of all this garbage, which is all completely wrong. And we're going to just plug this in here. And now we have a properly proven A implies C that all kind of falls out from the scope of this implication introduction rule. Great. And in fact, I think a lot of the complication of doing the incredible proof machine levels, or I think this logic generally, is keeping track of what your assumptions are and where did you make them. All right, we have A implies B, and we have A implies B implies C. From that, we're supposed to prove A implies C. Oh boy. Well, I think we're clearly going to need to introduce some implication. So let's connect that up there. Move that over here so you can read it. A implies C. So that means we're assuming A again. And we need to prove C. This one maybe isn't that hard. We're going to steal this A implies B. No, we're not using that yet. We want this. That gives us B implies C. So we could use, this is getting a little crowded. I apologize for that. We're going to reuse our assumption of A and this. And now we've got two things we've learned from assuming A. We've got our B implies C and we've got our B. So now we can use implication elimination to get a C, which is indeed the actual goal, the sub-goal there. That proves that A implies C. I don't know how you all feel about this, but I actually find this much more, this graphical, this visual approach to this, I find it a lot more intuitive than trying to do this algebraically. I know it's not really algebra, but I find it much simpler. Okay, given nothing, prove that A implies A. Oh, Ayn Rand would be proud. This one is clever. We take an implication introduction rule. We assume A, and if we assume it, we get to just introduce A equals A. Excuse me, now I'm doing it. A implies A. All right. Given A implies C, given B implies C, and given A and B, prove C. So now, this level, we're going to be combining, for the very first time, multiple types of introduction and or elimination rules. I think just elimination rules here. So we're going to eliminate the and, which gives us B. Right. And then we're going to eliminate this B implies C implication. And it implies A and B. So we can do either. I picked the wrong block, did I? Oh, there, that's right. B, C. Great. We're halfway through session 2. Given A implies C and given B implies C, prove that A and B imply C. This one's fun, and the reason this one is fun is because this feels like an obvious statement. Like someone asking you to prove this, you'd be like, well, of course, it's just intuitive, right? It's natural. And in fact, one terminology I've heard for this style of proof is natural deduction. It's a formal system meant to mimic the type of logic that we use going around our everyday lives. I want to say it was two names that are floating in my mind. I know I've read things are Richard Dedekind and someone, I know I'm pronouncing it wrong, Gerhard Gessen. I'm going to look that up right now. Gerhard Gensen. So it looks like this should be obvious, but you'll see it. It's actually going to take a little bit of work to get there. So one thing that I've kind of learned to recognize here is that this implication arrow over here is very different from these two. So I like to work backwards a little bit. I know that I'm going to need to introduce an implication to get to this at all. I'm going to need to introduce that implication that A and B imply C. And that means that I need to reach C, and it means I'm going to assume A and B. And so by kind of pulling those wires out a little bit, I find helps me think about what exactly is my goal and what is my sub-goal. So starting out, my sub-goal is to prove C. If I can prove C, then I'm done with the proof essentially, because of this rule here. When I have A and B, and I can eliminate that and that gives me separately A, and it gives me B. And I have these two implication rules that I can use freely because they are givens. So this time let's use the A. Oh, I plugged it into the wrong place. Do that a lot. And let's use our A implies C. And then we can hook our C, our free-floating C, up to that block, and that's it. We've proven it. So again, this statement, A implies B and B implies C, implies A and B imply C, is completely natural to me. It's so obvious that I don't even feel like I need to prove it. But what you see is, when you actually go to prove that formally, it's a little bit of work. Let's go on. Given B, prove A implies B. Right. This is demonstrating that you don't have to use your assumption to introduce your implication. This feels a little bit, I got to tell you, I've had this rule explained to me many times, and I'm I think it's very sus. Obviously, mathematicians are much smarter than me, so I guess I have to believe them, but this one is not intuitive to me. So I can assume A, and I'm trying to prove A implies B, and I've been given B, and I could just plug B into our implication introduction rule. I'm not sure that follows, because my natural language understanding of A implies B is that A is somehow causal, right? But this feels very close to me to the ex falso rule, where if you assume something false, you can improve anything. This is kind of the inverse of that. Like if I have something, I could say that anything else in the environment implies it. And I think that's the key. I think that we're working Strap in, folks. This is where I'm going to make a bunch of math nonsense that isn't true, and I'm going to make mathematicians angry. My understanding is that all of these implication rules are operating within what I, as a computer scientist, think of as an environment. I think it's usually referred to by the Greek letter capital gamma, right? And so this is saying that it's not that you can say that anything implies something you've been given. It's more like anything in gamma. It follows from the whole environment, not necessarily from that specific statement. All right. Please, yes, leave angry comments. I want to be corrected about this. Explain to me why I should not feel that this proof is sus. Given A and B imply C, prove that A implies B implies C. So, once again, we're clearly going to need to introduce some implications. And that's the theme of this level, really. And I think we're going to have to introduce several. So our first sub-goal is going to be to prove that B implies C given A. And we can figure this out mechanically, right? There are two implication symbols in our goal. So logically, we're going to have to introduce two implications. Okay. I'm not sure, though, what we're trying to assume here, right? We're trying to prove here that B implies C. So our secondary sub-goal is to prove C. And from that, we're going to assume B. Well, now we have A and we have B. I'm trying to be very careful about the word and, which is, a dangerous word when you're trying to do all this logic. So given that we have A and given that we have B, we can assume, we can use an AND introduction rule to demonstrate that we have A and B, and we have this implication rule here, so we can eliminate this implication to get C, which is what our sub-goal was, and thus we've completed this proof. Quod erat demonstratum. I'm probably pronouncing that wrong. QED. This is the complete inverse of the last proof. Given A implies B implies C, prove that A and B imply C. Well, again, these are not the same implication arrows. So let's go ahead. Yikes. Let's go ahead and what's our sub-goal? Our sub-goal is to get to C, and we get to assume A and B, which means we can eliminate that to get A standing alone and B standing alone. And I think we're going to have to eliminate. Yikes, we're going to use our assumption here. That gives us B implies C, and we will eliminate it again. That goes there. That goes there. We'll just draw a new line from here. And we've now proven the inverse. We're getting close. Looks like I'm going to need a little more room for this one. So let's make it zoom out a little bit. A implies B and A implies C implies A implies B and C. Okay. Well, first, I think we're clearly going to have to break this statement down. So let's break it down into A implies B and A implies C. Well, we don't have an A, so we're going to have to assume it, and the only real way we have to assume things right now is with this implication introduction rule, right? Let's in fact just assume that that's what we're trying to prove. Well, now we get to assume A, and our sub-goal is now B and C. So this looks pretty straightforward because we have A, so we can eliminate several implications. We can eliminate both of those using this A. And the wires here, the lines here, they're not wires, are going to get a little messy. I apologize. Now we have B and C, and we can just introduce an AND to join those. B goes there, C goes there, and that is in fact our sub-goal in our implication. That's proven. Our last level in session 2. I don't know how far I'm going to go today, but I'm going to try and go as far as I can. I am going to cut the video, as I said. We'll do session 3 in the next video, but let's do our last level for session 2. All right, we've got a bunch of implications, but the thing we're trying to prove does not have an implication at all, right? So that suggests to me that we want to be eliminating an implication at the end, and we have this A implies B. So it feels to me like the sub-goal is to prove A, or to obtain A, which will imply A implies B, which will imply B, right? So this is going to be like X implies B. So somehow we want to use this, right? And for this we need this bare A hanging out. And for this we need this bare A hanging out. But we don't have an A. But we do have A implies B implies A. So could I do something wild and crazy, like also use the A and B we will have proven from here, no, that's wrong. A implies B implies A. Right. Okay. Use that A and B there, which implies A. Now, I don't think we could use this A here to go back here, because that's circular logic. And we can see the wires, the lines turn red there. So. But this part of it is all semantically valid. So what are our sub-goals here? This needs an A. This is full. I think what we can do, maybe, is this is an A. We're going to get rid of this connection here where we're kind of escaping the bounds of our assumption. And this is going to be the A implies B that we need. This A implies B is going to go right. That's an A implies B. We can eliminate that implication there. That A goes there. There's a B. That implies that. Does that work? I feel like we've somehow... Right. The deal here is, this looks very confusing because my wires are terrible. I apologize. What we are trying to do here is you can prove A implies B to some extent, but the only way you can really use this elimination implication elimination rule is by assuming A. And so it's possible to structure this proof in such a way that your A implies B escapes the bounds. You want to make sure that the A implies B that you're using in the end here on the right-hand side of the proof actually came out of your implication introduction and was not derived directly from this, because this is a trap, because you can't prove this without assuming A. That is the final level of session 2 of the Incredible Proof Machine at incredible.pm. I think that took a lot longer than I thought it was. The difficulty ramps up pretty quickly. So we are going to continue. I think I have more in me. I'm going to see if I can go on and do session 3. I'm going to do that, though, in the next video. This has been Programming Like It's 1979. Thanks for watching.